All right, how do we find the inverse of a function? Well, before we jump into it, first let's talk about inverse relations. Those exist if and only if one relation contains AB when the other relation contains BA. So what does that mean? All right, well, here I have a graph of two parabolas. We've got this red parabola and this blue. All right, and these are inverse relations. So this red parabola, that's the parabola y is equal to x squared minus 4. The blue parabola is the equation x equals y squared minus 4. And you might remember about inverses that you just swap x and y. So here's what it means for it to be a relation. On this red graph, I can see the point 2, 0. So if I were to make a table, it has the point 2, 0. Well, then on the blue graph, I should be able to find the point 0, 2, which I can. It's right there. So whenever this had the point AB, this inverse relation had the point BA. And that's true for every single point on these. The reason that they'll always have the points A, B, and BA is because inverse relations are reflections over the line y equals x. And if you remember from geometry, every xy will become yx whenever you reflect over the line y equals x. But these are inverse relations. What does it mean to be an inverse function? You see, in this example, the inverse, this blue, it is not a function because it does not pass the vertical line test, right? We're mostly interested in functions that have inverse functions. For a function to have an inverse function, it must be 1-to-1. Well, what does that mean? You remember when we were talking about functions and we said in order for a relation to be a function, each input can only have one output. Well, to be 1-to-1, each output can only have one input. So this would be 1-to-1. Whereas this relationship over here is still a function, but it is not 1-to-1 since these two go to the same output. Now we're used to test if something is a function, we're used to using the vertical line test. And what the vertical line test does is it tests each input to make sure it only has one output. That's why I can only touch the graph one time at any time. Well, because we don't want to check if each input has an output, we want to check if each output has only one input, we can use the horizontal line test. And you see, a function will have an inverse function if the original function passes the horizontal line test. So this function will pass the horizontal line test, so it does have an inverse function. So because this function here, f of x, has an inverse function, we can say that f inverse of x exists. All right, go ahead and try it on your own. Will these functions have an inverse function? Use the horizontal line test to see if these would have an inverse. All right, and we should see that these two do not pass the horizontal line test, so they are not 1-to-1. That means that they are not invertible. Whereas this function does pass the horizontal line test, so it's invertible. It has an inverse. How do we go about finding an inverse function? Well, a function and its inverse swap their domain and range. So what does that mean to us? That means that we can just swap x and y and solve. All right, so let's try it. Here we have f of x equals x minus 1 over x plus 2. Now to solve, I'm going to start by just swapping x and y. So I'm going to say x is equal to y minus 1 over y plus 2. Now I'm just going to use my algebra skills to solve this. I'm going to multiply both sides by y plus 2. So xy plus 2x equals y minus 1. Now since I'm solving for y, I'm going to isolate those y terms. So I'm going to get the y's on the same side. xy minus y equals negative 2x minus 1. Here I can pull out a y to get x minus 1 is equal to negative 2x minus 1. And finally, just solve for y. I'll move this up here. Y is equal to negative 2x minus 1 over x minus 1. And then finally, my last step, I would really want to write this as f inverse of x is equal to negative 2x minus 1 over x minus 1. And any time that we have a rational, we go ahead and state the domain, for x not equal to 1, because we can't divide by 0. Now, to extend a point from earlier about them swapping domain and ranges, I want to look at these original graphs here. Notice that the domain of the original function, there's an asymptote right here at negative 2, and there's also one here at 1. So the domain is negative infinity to negative 2 union negative 2 to infinity. And the range was negative infinity to positive 1 union 1 to infinity. And now let's look at the asymptotes of our inverse. Right, we have right here at x equals 1, and we have this at y equals negative 2. So look at the domain and range. The domain of the inverse is negative infinity to 1 union 1 to infinity. And the range is negative infinity to negative 2 union negative 2 to infinity. The domain and ranges swapped. And we knew that this function had an inverse because it passes the horizontal line test. It is invertible. All right, you try. Find the inverse of f of x equals square root of x minus 4. And then in a second, we'll talk about why this one's a little special. All right, well, hopefully you got the inverse of f, so f inverse of x is x squared plus 4. But let's try to remember what these graphs actually look like. The square root of x minus 4 is a square root function moved right 4. Right, so its domain is 4 to infinity with a range of 0 to infinity. Whereas this x squared plus 4 is a parabola shifted up 4. Now, to be its inverse, though, this function's domain needs to have this function's range. So we can actually only use from 0 to infinity. So here we got to go back and say for x greater than or equal to 0. All right, verifying inverses. One thing that we should remember from Algebra 2 is that f and g are inverses of each other if f of g of x and g of f of x both equal x. So let's see an example of that. All right, here we have two functions. F of x equals 6 over x minus 4, and g of x is 6 over x plus 4. All right, so I'm going to find first f of g of x, which just means I'm going to just plug g right into f. So that would be 6 over x plus 4 minus 4. Well, here the 4's just subtract each other. So now we have 6 over x. That's the same as 6 times x over 6. 6 canceled, and we just get x. So f of g of x equals x. Now we have to check g of f of x. So that would be 6 over, plug in this entire function, 6 over x minus 4 plus 4. Remember, dividing fractions, that'd be 6 times x minus 4 over 6 plus 4. These 6's are going to cancel each other. X minus 4 plus 4 is equal to x. So because f of g of x equals x and g of f of x equals x, f and g are inverses of each other. Yay! And all right, that's going to wrap it up for these inverse notes. Goodbye.